What if the most peaceful lights in the night sky were hiding the most violent secrets in the universe? What if the calm stars above you, the same ones people have stared at for thousands of years, were concealing realities so extreme that human language can barely contain them? A dead star so dense that a single teaspoon of its matter would weigh billions of tons. A star with a magnetic field so violent it could tear apart the structure of atoms. A star that should have died billions of years ago, yet somehow burns with the brightness of youth. These are not fantasies. They are among the rarest objects ever discovered in the universe, and tonight we begin where the strangest truths in astronomy often begin, with a simple point of light that looks completely ordinary. That may be the most unsettling truth of all. The sky looks calm because distance hides violence, it hides collapse, it hides pressure so immense that matter itself changes identity. And hidden among those quiet lights are rare stars, the exceptions to the cosmic rulebook, the stars that reveal what the universe is truly capable of. Most stars are understandable. They are born from collapsing clouds of hydrogen and dust. They ignite fusion. They spend millions or billions of years converting hydrogen into helium, and eventually they die according to their mass. That is the ordinary story. But rare stars are what happen when the ordinary story breaks. They form when gravity becomes extreme, when binary companions interfere, when matter is stolen, when stars collide, or when the aftermath of death refuses to stay quiet. And those rare exceptions matter far more than their small numbers suggest. Because in astronomy, the strangest objects often carry the deepest truths. If you're here tonight, lying in the dark, carrying the weight of your thoughts through another long night, then this journey is for you. Not just because it is a journey into space, but because it is a journey into scale, into perspective, into the strange comfort that comes from realizing how vast and mysterious reality really is. Rare stars remind us that even the universe does not always follow its own simplest rules, and there is something strangely calming in that, something deeply human. Because perhaps you too know what it feels like to live outside the ordinary pattern, to feel like an exception in a world that expects rules. Rare stars are the universe's exceptions, and tonight we will wander among them slowly. We will explore stars that pulse with such precision they rival the best clocks humanity has ever built. We will examine stars so dense their interiors remain one of modern physics' greatest unsolved mysteries. We will meet stars whose magnetic fields are so powerful they can reshape the behavior of light itself, and we will see stars that appear younger than they should be, as though time itself failed to age them properly. These are not just strange astronomical objects, they are laboratories of impossible physics. A neutron star, for example, forms when a massive star dies in a supernova and its core collapses under gravity so intense that electrons and protons are crushed together into neutrons. What remains is an object often no larger than a city, but containing more mass than the Sun. The modern observations from gravitational wave detections, X-ray timing missions like NASA's NICER, and radio pulsar arrays have confirmed that these stellar remnants are among the densest known objects in the universe outside black holes. But even now, astronomers still do not know exactly what lies inside them. That uncertainty is astonishing. We can detect planets around distant stars. We can photograph the shadow of a black hole. We can measure the expansion of the universe. Yet inside a neutron star, matter enters a regime of density we still do not fully understand. That is what makes rare stars so important. They are not merely strange. They are unfinished scientific questions glowing in the dark. And that is the deeper purpose of this journey tonight. Not simply to learn what rare stars are, but to understand why they matter. Yeah, why astronomers spend decades chasing unusual signals from the sky. Why a strange pulse, an unusual spectrum, or a sudden flare can change our understanding of the universe itself. Because rare stars are where the rules of nature become visible under pressure. They expose the machinery beneath the surface of reality, and perhaps, as you listen tonight, you will begin to feel the strange comfort hidden inside that idea. That even in a universe governed by laws, there are still exceptions, still mysteries, still beautiful disruptions in the expected order of things. And if this journey brings you even a little peace tonight, if it helps quiet the noise of the day and carry your thoughts into softer places, a simple like on this video helps this quiet journey reach someone else who may need the same comfort beneath the same stars. For now, let your breathing slow. Let the room grow softer around you. Let the ordinary world become distant. And as the night deepens, imagine the sky not as a field of simple lights, but as a hidden wilderness of impossible survivors, collapsed monsters, ancient impostors, and strange cosmic relics. Because the universe is never as simple as it first appears, and the rarest stars are proof that the strangest truths are often hiding in the quietest places. The strangest part is not that some stars die. It is that death can make them more extraordinary than life ever did. Imagine a star collapsing so completely that the familiar architecture of matter simply breaks apart, not in fire, not in explosion, but under pressure so overwhelming that atoms themselves surrender. Not melt, not burn, surrender. Deep inside one of the universe's most violent endings, the empty space inside atoms disappears. The structure that defines ordinary matter is crushed into something far stranger. And what remains is one of the most unsettling objects in all of astrophysics, the neutron star. If an ordinary star is a furnace, a neutron star is a monument to pressure. It begins with a star far heavier than our Sun, usually at least 8 times more massive, spending millions of years fusing heavier and heavier elements in its core. Hydrogen becomes helium, helium becomes carbon, carbon becomes oxygen, layer by layer, element by element, until iron forms at the center. And iron is the end of the road. Unlike lighter elements, iron cannot release energy through fusion. It is dead weight at the center of a living star. And once enough iron accumulates, gravity wins. In less than a second, the core collapses inward at nearly a quarter of the speed of light. The outer layers crash inward, rebound violently, and explode outward as a supernova. But the core remains, and that core is where reality becomes almost incomprehensible. The pressure inside a collapsing stellar core becomes so intense that electrons are forced into protons, combining to form neutrons and neutrinos in a process called electron capture. The neutrinos escape. The neutrons remain. The result is an object made almost entirely of neutrons, packed together with no atomic structure left. A neutron star is often only about 20 kilometers across, roughly the size of a city, yet it can contain between 1 and 2 solar masses. Think about that. Yeah, more mass than the Sun compressed into something small enough to fit between distant towns on Earth. The density becomes almost absurd. Current models estimate that 1 cubic centimeter of neutron star material can weigh hundreds of millions of tons. A single teaspoon would weigh around 1 billion tons on Earth. That comparison is so extreme it almost stops being useful. It becomes abstract. But the physics behind it is very real. If such a spoonful could somehow be brought to Earth, which it could not survive doing, it would punch through the planet's crust under its own weight like a bullet through water. And yet, despite this violence, neutron stars are strangely stable. They do not collapse further because of neutron degeneracy pressure, a quantum mechanical effect that prevents neutrons from occupying the same state. It is one of the most elegant examples of quantum mechanics holding back gravity itself. a microscopic rule preserving a cosmic corpse, and even now astronomers are still learning what neutron stars truly are. Recent observations from NASA's NICER telescope, mounted on the International Space Station, have measured neutron star radii and masses with increasing precision, helping scientists narrow down the equation of state, the relationship between pressure and density inside these objects. But there is still uncertainty. Some models suggest exotic interiors containing hyperons, free quarks, or even phases of matter never observed anywhere else in the universe. That means neutron stars may be the only places where matter exists in forms beyond our current laboratory understanding. They are not just dead stars, they are active mysteries. Strange enough that their interiors may rewrite particle physics itself, and perhaps that is the most beautiful thing about them. Even after death, they continue teaching us. Their lives may have ended, but their existence remains an experiment in extreme reality, still unfolding in silence across the galaxy. A neutron star is proof that endings in the universe are rarely simple. Sometimes death compresses truth into its purest form, and in the case of these stellar remnants, truth becomes so dense that even light and time begin to behave differently around them, because the next thing neutron stars do is even stranger. Some of them begin to spin, and when they spin, they become the most precise clocks in the universe. A dead star should be silent. That feels like the natural expectation. A life ends, the fire goes out, and what remains fades slowly into darkness. But the universe rarely respects our expectations. Some neutron stars do not fade quietly at all. Instead, they begin spinning. And in that spinning, they become something almost impossible. Cosmic clocks so precise that they rival the finest timekeeping machines humanity has ever built. Imagine an object heavier than the sun, crushed into a sphere barely 20 kilometers wide, rotating hundreds of times every second. Not every minute, every second. The surface moves at astonishing speed, carrying enormous magnetic fields through space like spinning blades of invisible force. And when the magnetic poles are tilted away from the rotation axis, beams of radiation sweep outward like lighthouse beams across the darkness. If Earth happens to cross one of those beams, we detect a pulse, a signal, a beat, a rhythm. This is what astronomers call a pulsar. At first glance, the discovery of pulsars seems so unnatural that some scientists jokingly labelled the first signal LGM-1 for little green men. The pulse was too precise, too regular, too artificial in appearance. But the truth was stranger than alien intelligence. Nature had built its own perfect clock. Pulsars were first discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish through radio observations. Since then, thousands have been identified across the Milky Way, and what makes them extraordinary is not just their existence, but their reliability. Some pulsars rotate once every few seconds. Others, called millisecond pulsars, spin hundreds of times each second with astonishing stability. The fastest known pulsars rotate more than 700 times per second. May you think about that. Something with more mass than the sun compressed into a city-sized object spinning so fast it seems impossible that gravity can hold it together. But gravity does. And because of that, pulsars become nature's metronomes. Their timing is so exact that over long periods some lose less than a millionth of a second in accuracy. That is extraordinary. Modern atomic clocks remain the gold standard of precision, but pulsars approach that precision naturally, without engineering, without machinery, simply through physics. And astronomers use them in ways that feel almost poetic. By measuring the timing of pulsars across the galaxy, scientists can detect tiny disturbances in space-time itself. In 2023, multiple pulsar timing array collaborations, including Nanograv, reported evidence for a background of low-frequency gravitational waves ripples in space-time generated by supermassive black hole mergers across cosmic history. And how are those waves detected? By measuring tiny irregularities in pulsar timing. Imagine that! Dead stars acting as sensors for invisible waves moving through the fabric of the universe. Their regularity is what makes disturbance visible. That is one of the great lessons of pulsars. Precision reveals hidden motion. Stability reveals invisible change. And there is something deeply calming in that idea. In a universe of chaos, some objects keep perfect time. They spin, pulse, and repeat with unwavering discipline, as though the universe itself still remembers rhythm even after death. A pulsar is not a living star anymore. It no longer burns. It no longer fuses. Its fire is gone, and yet it remains active, broadcasting its presence across light years with every turn. Death did not silence it. It transformed it into time itself. But not all neutron stars choose precision. Some choose violence, because when magnetism becomes stronger than almost anything else in the universe, the dead star becomes something even stranger than a pulsar. It becomes a magnetar. If a pulsar is a clock, a magnetar is a weapon. It begins the same way, with the collapse of a massive star into a neutron star. But in rare cases, something far more extreme survives the collapse. A magnetic field so powerful that it becomes the dominant force shaping the star's behavior. To understand how strange this is, consider Earth's magnetic field. It guides compasses, shapes auroras, and protects life from solar radiation. It is powerful by human standards. A refrigerator magnet is stronger. But a magnetar is stronger than both by a factor so enormous that comparison almost becomes meaningless. Its magnetic field can reach 1 quadrillion Gauss. That is roughly 1 trillion times stronger than Earth's magnetic field, and it is the strongest magnetic field ever observed in the universe. If a magnetar passed halfway between Earth and the Moon, its magnetic influence could wipe data from electronic devices and distort atomic structures. At closer distances it would become lethal, but the magnetar itself is tiny, barely 20 kilometers across. A city-sized object carrying a magnetic force, powerful enough to dominate everything nearby. That contrast is one of the strangest in astrophysics. Small body, immense power. The physics of magnetars is still being studied, but astronomers believe they form when certain rapidly rotating massive stars collapse in such a way that their magnetic fields are amplified dramatically during the collapse. Like a cosmic dynamo concentrating unimaginable force into a tiny remnant. The result is not stability, it is tension. Magnetars live under magnetic stress so extreme that their crust can crack, and when it does, the energy released is staggering. These events are called starquakes. Similar in concept to earthquakes, but infinitely more violent. When the crust shifts, the magnetic field reconfigures suddenly, releasing enormous bursts of X-rays and gamma rays into space. In 2004, on one such giant flare from the magnetar SGR 1806-20 released more energy in a fraction of a second than the Sun emits in hundreds of thousands of years. Even from 50,000 light-years away, the flare was powerful enough to affect Earth's ionosphere. A dead star on the other side of the galaxy briefly touched our atmosphere. That is difficult to fully absorb. Distance usually feels like safety. Magnetars remind us that distance does not always mean isolation. These stars are so extreme that they challenge the boundaries of known physics. In their magnetic fields, atoms become distorted. Chemical behavior changes. Light itself can be polarized by empty space through quantum vacuum effects, something predicted by quantum electrodynamics and observed in magnetar environments. That means magnetars are not just astrophysical objects. They are laboratories for testing physics under conditions impossible to create on Earth. And perhaps most unsettling is this: magnetars do not last long. Their magnetic fields decay relatively quickly, over tens of thousands of years, which is brief in cosmic terms. That makes them rare, temporary, violent, like cosmic storms trapped in the bodies of dead stars. And yet, even in their violence, there is a strange beauty. A magnetar is a reminder that death in the universe does not mean peace. Sometimes death concentrates force. Sometimes collapse creates monsters more powerful than life ever was. And in the silent dark between the stars, those monsters wait under impossible tension, holding energy like loaded springs. But even magnetars are not the strangest stellar deception, because some stars do something even more unsettling. They pretend to be young in places where all youth should be gone. The unsettling thing about the universe is not that it creates strange objects, it is that sometimes it creates impossibilities. Stars that should be dead, but are not. Stars that should be old, but look young. Stars that appear to have escaped time itself. And nowhere is that mystery more visible than in the strange case of blue stragglers. Imagine entering a city where everyone is ancient, every building weathered, every street worn, every sign of youth long erased by time, and then, in the centre of it all, you find a handful of people in perfect youth, energetic, bright, untouched by age. That would feel wrong. In astronomy, blue stragglers create exactly that feeling. They are stars found inside ancient globular clusters, some of the oldest stellar populations in the universe, often more than 10 billion years old. In these clusters, all stars formed at roughly the same time from the same cloud of gas. That means the more massive stars should have lived fast and died long ago, leaving only smaller, older survivors behind. But blue stragglers break that pattern. They are hotter, brighter, and bluer than they should be. They look younger than the entire cluster around them, and that is the puzzle. They should not exist there, not in that form, not at that age. Their existence seems to violate one of the most reliable tools in astronomy, stellar aging. Normally, astronomers can estimate the age of a cluster by examining which stars remain on the main sequence. The heavier stars leave first, aging faster. But blue stragglers remain behind, Nososki, glowing as if they ignored the rules. For decades, astronomers debated how they formed. The leading explanation now is surprisingly intimate. Blue stragglers are not truly young, they are rejuvenated. In crowded star clusters, stars pass near each other far more often than in quieter regions of the galaxy. Sometimes two stars collide and merge into one larger star. When that happens, fresh hydrogen is mixed into the new core, effectively resetting part of the stellar clock. The merged star becomes hotter, heavier, and brighter. It looks young again. Another pathway is quieter, but equally strange. In binary systems, one star can steal mass from its companion. That stolen hydrogen acts like new fuel, extending its life and making it appear younger than its true age. In both cases, blue stragglers are stellar imposters, and old stars wearing the appearance of youth. Recent observations from the Hubble Space Telescope and high-resolution spectroscopy have strengthened this picture, revealing binary companions and collision histories hidden inside many blue stragglers. Their chemistry often carries traces of mass transfer or merger events, exposing their secret histories. And there is something deeply human in their story, because blue stragglers remind us that appearances can deceive. A bright surface can hide an old history. A youthful glow can be built from collision, loss, or theft. They teach astronomers caution. The visible face of a star is not always the full truth. Sometimes youth is only a costume stitched from older material, and perhaps that is why they feel so compelling. Because in the sky, as in life, history is not always visible from the outside. Some stars age honestly, others reinvent themselves, but blue stragglers are only one kind of deception, because some stars do something even stranger. Instead of hiding age, they strip away everything else, exposing their bare inner layers to the universe itself. Most stars hide their secrets beneath thick outer layers. The surface is only a mask, a glowing skin concealing the true machinery deep inside. Fusion happens far below, where pressure and heat transform matter into heavier elements. Normally, those inner layers remain hidden until the star dies, but some stars lose so much of themselves before death that their deepest layers become exposed while they are still alive. These are the Wolf-Rayet stars, and they are among the most violent stars the universe can make. If ordinary stars are living furnaces, Wolf-Rayet stars are the exposed engines after the outer casing has been torn away. They begin as massive stars, often more than 20 times the mass of the Sun. Their lives are short, fast and extravagant. Massive stars burn fuel at astonishing rates because gravity compresses their cores so intensely that fusion accelerates dramatically. What might take billions of years in a smaller star happens in millions here. But Wolf-Rayet stars enter an even stranger phase. Through fierce stellar winds, they begin shedding their outer hydrogen layers into space. These winds are not gentle. They can blow at speeds of more than 2,000 kilometers per second, stripping away matter continuously. Over time, the star peels itself open. What remains is not the familiar hydrogen-rich surface of an ordinary star, but deeper fusion layers rich in helium, nitrogen, carbon, and oxygen. Astronomers know this because of spectroscopy. Wolf-Rayet stars display unusual emission lines, signatures of exposed chemistry that should normally remain buried. In other words, these stars let us look inside stellar evolution while it is still happening. That alone makes them extraordinary, but their violence extends far beyond their surfaces. The winds from Wolf-Rayet stars slam into surrounding gas, carving giant bubbles in the interstellar medium, reshaping nebulae and flooding nearby space with harsh ultraviolet radiation. They do not simply exist in their environment, they attack it. Recent observations from the James Webb Space Telescope have revealed remarkable details in Wolf-Rayet systems, including pinwheel dust spirals created in binary systems, where colliding stellar winds condense carbon-rich dust into expanding spirals. These structures are not just beautiful, they are records of orbital motion written into space itself. And perhaps the most dramatic truth about Wolf-Rayet stars is this: they are close to the end. Very close, in cosmic terms. By the time a star reaches this stage, it has burned through much of its available fuel. The exposed fusion layers tell astronomers that the core is racing toward collapse. Some Wolf-Rayet stars are likely future supernovae, or even gamma-ray burst progenitors if conditions align. They are stars already preparing their own funerals. Their surrounding nebulae are often built from their own discarded matter, future shrouds waiting for the final explosion. That gives them a haunting quality. They are alive but visibly unraveling, powerful but doomed, and strangely beautiful because of that. A Wolf-Rayet star is what happens when a massive star becomes more revealing the more of itself it loses. It is proof that in astronomy, loss does not simplify. Sometimes loss exposes the most extraordinary truths, and if Wolf-Rayet stars are the stripped skeletons of stellar giants, then the next objects are stranger still, because some stars do not lose themselves. They steal from others to survive. Not every star survives by burning its own fuel. Some survive by stealing. That is one of the strangest truths in the sky. We often imagine stars as isolated lives, or each one born alone, living by its own internal fire and dying according to its own mass. But the universe is full of pairs. More than half of Sun-like stars are thought to exist in binary systems, and for massive stars that fraction may be even higher, which means many stellar lives are not solitary stories at all. They are relationships, and sometimes those relationships become violent. Imagine two stars orbiting so closely that gravity begins to distort their shapes. One ages faster, swells into a giant, and its outer atmosphere stretches outward until it crosses an invisible boundary called the Roche lobe, the region where gravity can still hold its own gas. Once that boundary is crossed, the gas is no longer loyal. It begins to flow toward the companion star, slowly at first, then relentlessly. This is mass transfer. And it changes everything. The receiving star gains fuel, mass, and often a second life. The donor star loses mass, structure, and sometimes its future entirely. What looks from a distance like two calm lights in the sky may actually be a cosmic theft, unfolding over millions of years. In some systems, the thief is an ordinary star, but in the stranger systems, the thief is a stellar remnant, a white dwarf, a neutron star, or even a black hole. These compact objects pull gas from their companions into spinning accretion disks, where friction heats the gas to extraordinary temperatures. The infalling matter becomes light, sometimes visible light, sometimes X-rays, sometimes violent eruptions. A white dwarf stealing hydrogen from a nearby companion can trigger nova explosions. Yes, sudden thermonuclear flashes on its surface that dramatically brighten the system without destroying the star. These are not rare events. Modern sky surveys like the Zwicky Transient Facility and Gaia have detected countless such outbursts, revealing how common stellar feeding really is. But neutron stars make the process even more extreme. Their gravity is stronger, their surface is denser, and the gas crashes down with astonishing violence, releasing powerful X-rays. In X-ray binaries, the brightness of the system often comes not from the star itself, but from the act of falling. That is one of the strangest reversals in astronomy. The light is not born from fusion, it is born from theft. Some of the most powerful X-ray sources in the Milky Way are not stars living normally, they are stars consuming others. And over time, the relationship changes both partners. The donor star may be stripped nearly naked, reduced to a faint remnant. The compact thief may gain mass, spin faster, or even be pushed toward catastrophic collapse. In some cases, this theft may eventually trigger a Type 1a supernova, when a white dwarf grows too heavy and detonates entirely. So the theft is not just survival, it can be preparation for death. These systems matter deeply to astronomers because they reveal how stars evolve together. They show that companionship can rewrite destiny. A star's fate is not always decided at birth. Sometimes it is decided by whoever lives beside it, and there is something deeply unsettling in that. The universe is full of relationships where closeness means transformation, sometimes nourishment, sometimes destruction, sometimes both. A star can survive by taking from another. It can become brighter because something else grows dimmer, and in that exchange a new kind of stellar life emerges. But there are stranger relationships still, because in some systems, the compact survivor does not merely feed. It slowly destroys the very companion that once kept it alive. Some stars do not just steal from their companions, they consume them slowly, patiently, almost cruelly. If Chapter 7 was about cosmic feeding, this is about cosmic erosion. Black widow pulsars are among the most ruthless relationships in the universe, and their name is no metaphor. It is almost exact. A black widow pulsar begins as a neutron star, usually spun up into extraordinary speed by stealing matter from a companion over long periods. That process transfers angular momentum. You're winding the neutron star into a millisecond pulsar, a stellar remnant spinning hundreds of times each second. During that feeding phase, the companion is the source of life. Its gas feeds the neutron star, reviving it, accelerating it, strengthening its pulse. But eventually something changes. The feeding slows, the accretion disk fades, and the neutron star awakens fully as a pulsar. It turns on, and once it does, the relationship reverses. The pulsar begins blasting intense radiation and a stream of energetic particles outward. That radiation strikes the companion directly, heating its surface, stripping away gas, and slowly evaporating it into space. In some systems, the companion star is reduced to only a few % of the Sun's mass, a stellar skeleton barely surviving under constant assault. Astronomers call them black widow systems because the pulsar is effectively destroying the partner that once sustained it. It is a brutal inversion. The victim becomes the prey after serving its purpose. One of the best studied examples is PSRB 1957+20, the original Black Widow pulsar discovered in 1988. It spins more than 600 times per second and is actively stripping its tiny companion through intense pulsar wind. Modern radio and gamma ray observations continue to study these systems, revealing eclipses caused by escaping gas and showing the process in action. These are not theoretical stories. They are visible destruction unfolding in real time, and the process may end with total disappearance. If enough mass is lost, the companion may vanish entirely, leaving behind an isolated millisecond pulsar, the final survivor of a relationship that consumed itself. Imagine that. A star erased by proximity. A life ended not by age, not by explosion, but by staying too close to a dead star reborn as a weapon. Black Widow systems matter scientifically because they reveal transitional phases in pulsar evolution. They show how neutron stars switch between feeding and emission states. Some even blur the line between X-ray binaries and radio pulsars, switching identities over observational timescales. That means astronomers are not just observing strange objects, they are watching stellar evolution happen in motion. But beyond the science, there is something haunting about them. A Black Widow pulsar is a survivor that weaponizes survival itself. First, it depends on its partner, then it destroys it. The same relationship that gave it life becomes the source of the other star's death. It is one of the most intimate tragedies in astronomy, and perhaps one of the clearest reminders that in the universe, closeness is not always comfort. Sometimes closeness is fate. Sometimes gravity does not bind for peace. It binds for transformation. And if Black Widow pulsars are ruthless, the next stars are stranger in a quieter way. Because some stars vanish from sight, not because something destroys them, but because they hide themselves behind dust they create with their own dying breath. Some stars disappear without dying. That sounds impossible at first. In astronomy, when something vanishes, we expect catastrophe, a collapse, an explosion, an ending. But some stars simply fade from sight, not because their fire has gone out, but because they have hidden themselves behind material of their own making. Imagine a star becoming its own curtain, creating the very dust that blinds us to its light. That is the strange life of carbon-rich variable stars, and few are stranger than the rare Coronae borealis stars. Most stars change brightness for understandable reasons. They pulse, they eclipse, they rotate, their light follows patterns. But our Coronae borealis stars behave differently. They can shine steadily for years, even decades, and then suddenly plunge in brightness by factors of hundreds or thousands, almost as though someone switched them off. But the star itself has not changed much. It has simply disappeared behind a fresh cloud of carbon dust it created itself. These stars are hydrogen-poor and carbon-rich, an unusual chemical makeup that already marks them as rare. Their outer atmospheres contain enough carbon that, under the right conditions, carbon atoms can condense into soot-like dust close to the stellar surface. When that dust drifts into our line of sight, the star dims dramatically. Over time, the dust disperses and the star returns. Then it may happen again and again. The process feels almost theatrical, a celestial disappearance act performed by the star's own atmosphere. The prototype R Coronae Borealis has been observed for centuries, astonishing astronomers with its unpredictable fading. Modern infrared telescopes have revealed these dust clouds in exquisite detail, confirming that what looks like disappearance is really self-made obscuration. In recent years, with missions like James Webb Space Telescope and Gaia spacecraft have improved our understanding of dust production in evolved stars, showing how common stellar dust formation may be in late-life phases. But our Coronae Borealis stars remain among the most dramatic examples, and the deeper mystery is how they form at all. Current evidence suggests that many may be the result of white dwarf mergers, two dead stellar cores combining into one strange, reborn object. If true, that means these stars are already products of one stellar death before entering this strange dusty life, a star born from death, hiding behind its own ashes. There is something hauntingly beautiful in that. The same carbon dust that blocks their light is also one of the great ingredients of the universe. Carbon-rich dust expelled by dying stars eventually drift into interstellar space, becoming part of future stars, planets, and perhaps even living chemistry. The dust that hides the star today may become part of another world tomorrow. So even in disappearance, these stars are creating futures. They remind us that fading is not always ending. Sometimes fading is transformation. Sometimes what vanishes from view is simply preparing to become something else. And perhaps that is one of the quiet comforts of the universe. A star can hide itself and still remain. A star can disappear and still be there, waiting for the dust to clear. But there are stars even stranger than that. Stars that do not merely hide their surfaces, but reveal their exposed cores long before death ever arrives. Most stars die before revealing their deepest layers. Their outer shells remain intact until the final collapse or final shedding. The inner engine stays hidden, buried beneath hydrogen and helium for almost the entire visible life of the star. But some stars lose their outer identities early. Stripped bare by a companion, they reveal their inner hearts while they are still alive. These are stripped stars, stellar cores exposed before their natural time, and they are among the clearest examples that stars do not always evolve alone. Imagine taking a star and peeling away its outer hydrogen envelope, not by wind, not by explosion, but by gravitational theft from a nearby companion. What remains is smaller, hotter, and chemically stranger than the star once appeared. The bright outer personality is gone, the engine is visible. Look, these stripped stars are often dominated by helium because the hydrogen-rich outer layers have been removed, exposing deeper fusion zones. That is why many are called helium stars. In a normal stellar life, these layers would remain hidden until the final chapters. But binary interaction changes the script. In close binary systems, one star can swell into a giant and overflow its Roche lobe, transferring mass outward. If enough is lost, the core is exposed. From the outside, it looks like an entirely different kind of star, smaller, hotter, bluer, and far more compact. Yet it is the same star, just stripped of disguise. Recent work using the Hubble Space Telescope and transiting exoplanet survey satellite has helped identify more stripped star candidates, often hidden in binary systems where the brighter companion masks them. Their spectra betray them, revealing helium-rich surfaces and temperatures far higher than expected for their size. These stars matter enormously because they may be the missing ancestors of several important cosmic events. Some strip stars are thought to be progenitors of Type 1b and Type 1c supernovae, explosions where hydrogen is absent from the spectrum because it was removed long before the final collapse. That means strip stars are not just strange in themselves. They may be the setup for future cosmic violence. They also help explain how certain neutron stars and black holes form inside binary systems, preserving the partnership instead of destroying it completely. In other words, stripping changes not just the star but the future of the entire system. What makes these stars emotionally compelling is their honesty. Most stars wear layers. These do not. Their surfaces are not masks but exposed interiors, chemical truths laid bare in light. It is like seeing the machinery inside a clock while it is still running, and there is something intimate in that. A star usually keeps its deeper story hidden. A stripped star does not have that luxury. It carries its internal history openly, visible to anyone who knows how to read starlight. In astronomy, that makes them treasures, because every exposed layer is evidence of theft, of companionship, of interference, of a life rewritten by another star's gravity. And that may be one of the great themes of rare stars. They are often not born strange. They become strange through relationship, pressure, and loss. A stripped star is proof that identity in the universe is fragile. Remove the outer layers, and the deeper truth emerges. But some stars take that idea even further, because a few rare objects may be hiding something impossible at their centers. Not a normal stellar core, but a dead neutron star buried inside a giant living star. There are strange stars, and then there are stars that sound like mistakes in reality. A giant star with a neutron star hidden inside its core sounds less like astrophysics and more like science fiction. Yet the idea is real enough to have occupied serious astronomers for decades. These hypothetical objects are called Thorne-Jitkoff objects, named after physicists Kip Thorne and Anna Jitkoff, who first described them in the 1970s. And if they exist, they may be among the strangest stars the universe has ever made. Imagine a neutron star, the crushed remnant of a supernova, wandering too close to a red supergiant companion. In some binary systems, the orbit decays. The neutron star spirals inward, deeper and deeper, until it is swallowed by the giant's outer layers. Normally, we might expect total destruction, but under certain conditions, the neutron star may survive the plunge and settle into the center of the giant instead of tearing it apart. From the outside, the object might still look like an ordinary red supergiant, large, cool, swollen, and glowing with familiar red light. But inside, everything would be different. At the heart of the giant would sit a neutron star, an object only about 20 kilometers wide, carrying more mass than the sun, embedded inside an envelope hundreds of millions of kilometers across. That means the heart of the star would not be a normal fusion core at all. It would be a collapsed stellar corpse, altering the flow of energy, pressure, and nuclear reactions around it. This matters because the physics inside such an object would be exotic. Material falling onto the neutron star could trigger unusual nuclear pathways, producing chemical elements in strange abundances not expected in ordinary stars. That gives astronomers a way to search for them. If the chemistry at the surface looks wrong, too rich in certain heavy elements like lithium, rubidium, or molybdenum, it might be evidence of one of these hidden stellar hybrids. In 2014, astronomers identified a candidate called HV2112 in the Small Magellanic Cloud, based on unusual spectral chemistry. Later observations complicated that claim, and debate continues. That uncertainty is part of the fascination. We may already have seen one and not know it for sure. That possibility is thrilling, because it means one of the most bizarre objects in the universe could be hiding in plain sight, disguised as something familiar. That is one of astronomy's recurring lessons. Appearances deceive. A red giant may not always be a red giant in the simple sense. It may be a living shell built around a dead stellar core, a corpse wearing a living body. And what makes Thorne-Żytkov objects so haunting is their contradiction. Life and death coexisting inside the same star. A living envelope powered by a dead remnant. Fusion and collapse sharing the same structure. They are reminders that the universe does not always separate categories neatly. Sometimes the aftermath of death becomes the engine of a new and stranger existence. And if that sounds impossible, the next stars are no less unsettling. Because some stars look like they're exploding, brightening, erupting, hurling matter into space, yet somehow survive the blast. Most explosions in astronomy are final. A supernova is the end of a star's visible life, the catastrophic collapse or thermonuclear destruction that leaves behind a remnant or nothing at all. That is why it is so unsettling when a star erupts like a supernova and survives. It feels like witnessing death, only to discover it was rehearsal. These events are called supernova imposters, and they blur the line between instability and catastrophe in one of the strangest ways in stellar physics. A supernova imposter is a massive star that undergoes a giant eruptive outburst, becoming dramatically brighter and throwing huge amounts of gas into space, yet without destroying its core. The star remains alive afterward. From a distance, the event can resemble a true supernova, bright, violent, sudden, but the ending never arrives. It is not death, it is a warning. The most famous example is Eta Carinae, one of the most unstable and luminous stellar systems in our galaxy. In the 19th century, Eta Carinae underwent what astronomers now call the Great Eruption. For a time, it became the second brightest star in the night sky. Despite being more than 7,000 light-years away, it hurled out an enormous amount of mass, perhaps 10 to 20 times the mass of the Sun, creating the vast homunculus nebula we still see expanding today. And yet the star survived. That is extraordinary. An eruption powerful enough to mimic stellar death but not complete it. Modern observations from Hubble Space Telescope and James Webb Space Telescope continue to study Eta Carinae's surrounding nebula, revealing shock fronts, dust structures, and evidence of repeated instability. These observations suggest that massive stars can lose huge fractions of their mass in violent episodes before the final collapse. In other words, death may come in stages. That changes how astronomers think about massive stellar endings. Instead of one clean final event, some stars may lurch toward collapse through a sequence of giant convulsions, shedding layers, destabilizing themselves and reshaping the space around them long before the final supernova. That means some supernova may be preceded by years or decades of visible warning signs. Modern sky surveys like Zwicky Transient Facility and the Vera C. Rubin Observatory are now designed to catch these warning stages in real time. Imagine seeing a star practice its own destruction. That is what supernova imposters may be. A rehearsal for an ending not yet complete, and there is something strangely moving in that. A star convulsing under the pressure of its own instability, shedding pieces of itself, surviving each outburst, but growing closer to the inevitable. Not gone, not safe, suspended between life and death. The universe is full of transitions like this, places where categories blur. A star can look dead and still live. It can look alive and already be collapsing. Rare stars teach us that endings are often not clean. They are layered, messy, repeated, and in that way perhaps more honest. But some stars do not rehearse for death at all, and some survive by changing identity entirely, becoming clocks, weapons, thieves, ghosts, or even something colder and stranger than fire itself. Most people imagine death as an ending. In the universe, death can be much slower than that. Some stars die and keep changing for billions of years, becoming stranger the longer they cool. White dwarfs are one of the clearest examples. They are the leftover cores of stars like our Sun, compact and hot, no longer powered by fusion, glowing only because of stored heat. At first they seem simple, a stellar ember slowly fading. But deep inside, something extraordinary begins to happen. As a white dwarf cools, the atoms in its dense interior slow down. The pressure remains immense, the matter tightly packed, and eventually the ions begin arranging themselves into ordered structures. The star starts to crystallize, not like a gemstone in the ordinary sense, but like a giant cosmic lattice forming inside a dead stellar core. Imagine an Earth-sized object, carrying nearly the mass of the Sun, slowly freezing from the inside out over billions of years. That is what happens. The heart of the dead star becomes solid. This process changes the way the star cools. Crystallization releases heat, slowing the fading process. That means some white dwarfs stay warmer longer than expected, allowing astronomers to detect this effect. It is one of the strangest endings in stellar evolution. A star does not simply die and fade, it slowly turns into a crystal world in darkness. There is something strangely peaceful about that. After millions or billions of years of burning, collapsing and shedding its outer layers, here the final act is silence and order, a chaotic life ending in structure, a furnace ending as crystal. And perhaps the strangest part is this. The universe is not yet old enough for any white dwarf to have fully cooled into darkness. Every white dwarf ever formed is still carrying heat from its former life. Even in death, they are not finished. But some stars do not cool quietly. Some steal too much from a companion and destroy themselves in one final flash. Sometimes the most dangerous thing in the universe is generosity. A white dwarf is usually stable. It sits quietly after shedding its outer layers, cooling for billions of years. But in a binary system, stability can be broken by a nearby companion. If that companion gives too much, the white dwarf can die in one of the brightest explosions in the cosmos. This is the Type 1a supernova. It begins with theft or perhaps gift, depending on how you look at it. A nearby star loses gas. The white dwarf pulls it in, hydrogen piles up, more mass arrives, more pressure builds, and unlike an ordinary star, the white dwarf cannot expand to release that pressure. It is supported by quantum mechanics, by electron degeneracy pressure. That strange support system creates a deadly trap. As the mass approaches a critical limit, the temperature in the core rises, carbon fusion ignites. But instead of balancing itself like in a living star, the reaction runs wild. In seconds, the entire white dwarf detonates. Completely. No remnant survives. The star is erased. For a short time, it can outshine an entire galaxy. And what makes these explosions so important is their consistency. Because they reach similar brightness levels. Astronomers use them as cosmic measuring tools, helping map the expansion of the universe itself. In fact, these explosions helped reveal one of the greatest discoveries in modern cosmology, that the universe is expanding faster over time. That means the death of one star helped uncover the existence of dark energy. There is something beautiful in that, a quiet stellar remnant, pushed over the edge by closeness, becoming one of the brightest signals in existence. A final act so powerful it helps measure the cosmos itself. A star that spent billions of years fading, only to vanish in a burst of impossible light. But some stars do not vanish when they erupt. Some flare again and again, trapped in a cycle of repeated fire. Most explosions in the universe happen once. A star dies, A blast expands and the story ends. But some stars refuse to stay simple. They erupt, survive, and then erupt again. Like a wound reopening across time, these are recurrent novae, and they are among the strangest examples of repetition in stellar astronomy. The setup begins with a white dwarf and a nearby companion star locked in close orbit. Gravity slowly pulls hydrogen-rich gas from the companion, and that gas settles onto the white dwarf's surface. Layer by layer, it builds, quietly, invisibly, until pressure and temperature become unbearable. Then suddenly fusion ignites across the surface in a runaway flash. The system brightens dramatically. The outer layer is blasted into space, but unlike a supernova, the white dwarf survives. And then the process begins again. That is what makes recurrent novae so fascinating. They are not singular deaths. They are repeating instability, a cycle of theft, accumulation, fire, and reset. Some repeat over decades, others over centuries. Each eruption is a reminder that not all stellar violence is final. Some stars live inside patterns of destruction. They burn borrowed fuel like a fuse that keeps being relit. There is something deeply rhythmic in that. A cycle of tension and release written into starlight. It reminds us that in astronomy, endings can become habits. But there are stranger pairs still, because some binary systems combine two completely different chapters of stellar life into one household. Some stars look like contradictions, one old and swollen, one dead and compact, sharing the same space like two incompatible phases of life forced into one relationship. These are symbiotic stars, and the name sounds peaceful, but the reality is far more unstable. In a symbiotic system, one star is usually a red giant, bloated, cool, and slowly losing gas through stellar wind. The other is often a white dwarf, small, dense, and hungry. The giant sheds material. The white dwarf captures part of it. Between them forms a shared environment of gas, radiation, and slow-motion theft. What makes these systems strange is their dual personality. One part of the system is ancient and cool. The other is hot and violent. Spectroscopy reveals both at once. Cool stellar atmospheres mixed with intense high-energy emissions. It is like looking at youth and death layered together. Sometimes the white dwarf grows unstable from the captured gas and erupts in nova-like flashes. Sometimes the radiation ionizes the giant's wind, making the whole system glow in strange ways across many wavelengths. These stars are laboratories of interaction. They show how stellar lives overlap, interfere, and reshape one another. A giant approaching death feeds a dead remnant that can flare back to life. That reversal feels almost poetic. One star fading, the other reigniting. A shared system where one ending becomes another beginning. And perhaps that is the deeper lesson of symbiotic stars. In the universe, lives do not always remain separate. Sometimes one star's decline becomes another star's energy. Sometimes endings are shared. But some systems hide their true violence completely, because their brightest light is invisible to human eyes. Some of the most violent stars in the universe look almost ordinary if you use your eyes alone. That may be one of astronomy's strangest lessons. The visible sky is incomplete. Human vision evolved for sunlight, for survival on Earth, for a narrow slice of reality. But the universe is far larger than what eyes can see, and some stars save their most violent stories for invisible light. X-ray binaries are perfect examples. At first glance, they may appear unremarkable, just another star in the night. But hidden behind that ordinary glow is one of the most extreme engines in nature. These systems usually begin with a compact remnant, a neutron star or black hole, and a normal companion star orbiting nearby. Gravity does the rest. Gas is pulled from the companion, and spirals inward, forming an accretion disk. At first, the process sounds gentle, matter simply falling, but falling in space can be one of the most violent acts in physics. As the gas spirals closer, friction and gravity heat it to millions of degrees. At those temperatures, it no longer glows in visible light. It shines in X-rays. That means the brightest part of the system is hidden from human sight entirely. To our eyes, it looks ordinary. To X-ray telescopes, it becomes a storm. This changes how we think about stars. Not all stellar brightness comes from fusion. Sometimes brightness comes from gravity itself. Matter falling inward becomes energy, often with astonishing efficiency. In some black hole systems, the energy released per kilogram of infalling gas exceeds what nuclear fusion could produce. Gravity becomes the engine. That is one of the strangest reversals in astrophysics. The star does not shine because it lives, it shines because something is dying into it. Some X-ray binaries pulse if the compact object is a neutron star. Others flicker unpredictably as the accretion disk becomes unstable. Some erupt dramatically and then fade into quiet for years before flaring again. Their behavior feels restless, almost nervous, as though the system itself cannot settle. What makes these systems scientifically important is that they allow astronomers to study matter under extreme gravity. The disk near a black hole, for example, can approach the event horizon itself. There, space and time bend so strongly that the light carries the signature of relativity. By studying those signals, scientists can test Einstein's theory in some of the harshest environments in existence. And there is something emotionally strange about that. A star that seems calm in the sky may be hiding invisible violence. A quiet point of light may contain a storm hotter than the core of most stars. It reminds us again that appearances deceive. The universe often hides its greatest intensity behind ordinary surfaces, and perhaps that feels familiar. How often does reality hide its most powerful truths beneath calm appearances? X-ray stars teach us that what looks peaceful may contain unimaginable pressure. But even these systems are not the final evidence of stellar death. Because sometimes the star itself is gone, and all that remains is the wreckage. And sometimes the wreckage tells the story better than the star ever could. Some stars are remembered not by their lives, but by their ruins. Imagine a star so powerful in death that its debris remains visible for thousands of years after the star itself has vanished. The star is gone, but the evidence remains, spread across space like the aftermath of an ancient crime. These are supernova remnants, the ghostly remains of exploded stars. They are some of the most beautiful objects in astronomy, but their beauty comes from violence. When a massive star explodes, it hurls its outer layers into space at millions of kilometers per hour. The gas expands outward, slamming into surrounding material, heating it, shocking it, and making it glow. What remains is not one clean shell, but tangled filaments, glowing knots, expanding arcs, and strange structures shaped by both explosion and environment. Each remnant is a frozen history of destruction. The most famous example is the Crab Nebula. Nearly 1,000 years ago, human observers saw a bright new star appear in the sky. It was visible even during the day. What they witnessed was a supernova. Today, the remnant still expands outward, carrying the evidence of that event through space. At its center remains a pulsar, the dead core of the exploded star still spinning, still alive in its own strange way. That combination makes supernova remnants fascinating. They preserve both death and survival at once. The body of the star is gone, the heart remains. These remnants matter because they recycle the universe. Heavy elements forged inside stars are thrown into interstellar space through supernova explosions. Iron, calcium, oxygen, silicon. Many of the elements that make planets, oceans, and even human bodies were once inside stars like these. A supernova remnant is not just wreckage, it is redistribution. The universe taking one life apart to build future worlds. That idea carries strange comfort. Destruction as creation. Endings becoming raw material for beginnings. Even the chaos inside the remnant can trigger new star formation as shockwaves compress nearby gas clouds into collapse. One death starting many lives. But scientifically, supernova remnants are also laboratories. Their shockwaves accelerate particles to enormous energies, creating cosmic rays that travel across the galaxy. Their expanding gases reveal chemical maps of stellar interiors. Their central remnants, neutron stars or black holes, show what survives after collapse. Astronomers read them like detectives read a crime scene. Every filament, every chemical signature, every expanding shell tells part of the story. That makes them strangely intimate. The star itself may be gone, but its history remains visible. And perhaps that is one of the deepest truths in astronomy. Disappearance does not mean absence. A star can vanish and still shape the universe long after. Its body becomes cloud, its heart becomes remnant, its chemistry becomes future worlds, its death becomes visible architecture in space. The sky is full of these ghosts, still glowing from violence long past. But some stars do not need to explode to become strange. Some are strange simply because they should not exist at all. And those may be the most revealing stars of all. There are stars so old that they feel like memories from the beginning of time, and yet somehow they are still here, still burning, still carrying secrets from an era when the universe itself was young. That is what makes ancient metal-poor stars so unsettling. They are survivors from a cosmic childhood that should feel unreachable, and yet their light still arrives tonight. In astronomy, everything heavier than helium is called a metal. Carbon, oxygen, iron, gold. These are all metals in the language of stars, but the first stars in the universe had almost none of them. They were born from nearly pure hydrogen and helium, the simplest elements left after the Big Bang. Only after generations of stars lived and died did heavier elements spread through space. That means the oldest surviving stars should contain very little metal. They are chemical fossils, time capsules made of light. When astronomers study these stars, they are not just studying age, they are studying ancestry. Some of these ancient stars are more than 13 billion years old, meaning they formed not long after the universe itself began. They have survived almost the entire history of cosmic evolution. Think about that. Before Earth existed, before the Sun formed, before our galaxy fully settled into its shape, these stars were already shining. That makes them some of the oldest visible objects in existence. And what makes them rare is not only their age, but their chemistry. Their atmospheres preserve the elemental fingerprints of the earlier supernova, the first stellar deaths that seeded the universe with complexity. By studying those fingerprints, astronomers can reconstruct what the earlier stars may have been like, even though those first stars are long gone. These ancient survivors are like libraries written in atoms. Their iron content can be thousands of times lower than the Sun's. Some contain strange enrichments of carbon, suggesting the earlier stellar explosions may have been more complicated than once believed. They force scientists to revise models of the early universe again and again. That is the power of old stars. They are witnesses. And perhaps there is something deeply calming in that. A star can survive nearly the entire history of the universe. It can endure collisions, galactic migrations, radiation storms, and the rise and fall of countless neighbouring stars and still remain. Still shine. Ancient stars remind us that time in the universe is vast beyond feeling. Human life is brief, but the sky carries memory far older than thought itself. These stars are not just old, they are living history, But not all strange stars survive by age alone. Some survive by speed, moving through the galaxy so fast they may one day escape it entirely. Most stars stay close to home. They orbit the center of the galaxy in predictable paths, moving with the slow rhythm of cosmic order. But some stars have been violently thrown from their homes, launched into space like cosmic bullets. These are runaway stars, and they carry the memory of violence in their motion. Imagine a star moving so fast that it tears across the galaxy at hundreds of kilometers per second, faster than most of its neighbors, faster than the calm order of the Milky Way would normally allow. That speed has to come from somewhere, and usually it comes from disaster. One common origin begins in binary systems. Two stars live in close orbit for millions of years. Then one explodes as a supernova. The explosion destroys the balance instantly. The surviving companion is no longer held in orbit. It is flung outward at its orbital speed, shot into space by the sudden loss of its partner. A relationship broken by death becomes motion. Another pathway is even stranger. In crowded star clusters, close gravitational encounters between multiple stars can act like slingshots. One star loses energy, another gains it, sometimes enough to escape the cluster entirely. In rare cases, stars passing near the supermassive black hole at the center of the galaxy can be accelerated to such enormous speeds that they may escape the Milky Way forever. These are hypervelocity stars, exiles of gravity. What makes runaway stars fascinating is that their motion tells a story. By tracing their path backward, astronomers can sometimes identify where they came from. A broken binary, a dense cluster, a galactic center encounter. Their speed becomes evidence. Their direction becomes memory. A runaway star is a life still moving because of something violent long ago. And there is something strangely emotional in that idea. A star carrying trauma as momentum. A past event still shaping its future path. It reminds us that movement is not always freedom. Sometimes movement is the result of being pushed. But runaway stars also reveal something hopeful. Even after being thrown into the dark, they continue. They burn. They survive. They carry their light into emptier regions of space. Their loneliness becomes their journey. And perhaps that is the deeper beauty of them. Not all paths are chosen. Some are inherited from violence, from endings, they're from disruption. Yet the star keeps going, still bright, still alive, still moving forward into the unknown. But there are stars stranger than travelers, because some stars do not race through space. Some vanish into it so completely that they almost stop being stars at all. Not every star succeeds at becoming a star. That may be one of the strangest truths in the universe. We often imagine starbirth as inevitable. A cloud collapses, pressure rises, fusion begins, and a star is born. But sometimes the process stops just short of ignition. Gravity gathers the gas, the object forms, it glows faintly with heat, but the core never becomes hot enough to sustain hydrogen fusion. It is born almost as a star, but not quite. These are brown dwarfs, the failed stars of the cosmos, and in many ways, they are stranger than ordinary stars because they live in the space between categories, too massive to be planets, too small to be stars. Brown dwarfs usually form like stars from collapsing clouds of gas, but their mass stays below the threshold needed for sustained hydrogen fusion, about 8% of the Sun's mass. That small difference changes everything. Without stable fusion, they never achieve the long-burning life of true stars. Instead, they spend their existence cooling slowly, radiating away leftover heat from their formation. In youth, they can be surprisingly hot, glowing red or infrared, but over billions of years they fade toward darkness. They are stellar almosts, cosmic near misses, and yet they are not lifeless. Some can briefly fuse deuterium, heavier form of hydrogen, for a short time. The more massive ones may even fuse lithium for a while, but those are temporary sparks, not true stellar life. What makes brown dwarfs so fascinating is how hidden they are. Most are too dim for ordinary observation. They glow mainly in infrared, invisible to human eyes. That means our galaxy may contain far more of them than we once believed. Silent bodies drifting through the dark between stars. Some wander alone, some orbit stars, some even have weather, with cloud systems made of hot silicates and iron droplets falling through strange atmospheres. Imagine weather made of molten metal. That is not science fiction. That is the climate of a failed star. There is something deeply humbling in brown dwarfs. They remind us that nature does not always complete the path it begins, and some things stop just short of transformation and remain suspended between identities. Not stars, not planets, something in between. But even stranger than failed stars are stars so light, so cold and so dim that they challenge the idea of what a living star should even look like. If giant stars feel dramatic, red dwarfs feel patient. They are the smallest true stars capable of sustaining hydrogen fusion, and they are by far the most common stars in the universe. Yet they are so faint that none are visible to the naked eye from Earth. The sky is full of them, hidden in plain darkness. That alone feels strange. The most common stars in existence are almost invisible to us. Red dwarfs are small, often only a fraction of the Sun's mass and much cooler. Their surfaces glow with a deep reddish light, giving them their name. But what makes them extraordinary is not brightness, it is endurance. Large stars burn fast and die young. Red dwarfs burn with extreme efficiency. Because their interiors are fully convective, hydrogen is mixed throughout the entire star, allowing almost all of it to be used as fuel. Nothing is wasted. That makes their lifespans almost unimaginable. The smallest red dwarfs can live for trillions of years, far longer than the current age of the universe. In fact, the universe is not old enough for a single red dwarf to have died naturally yet. Every red dwarf ever born is still alive. Think about that. Entire generations of giant stars have been born, burned, exploded and vanished, while the smallest stars simply continue, quietly consuming their fuel with endless patience. They are the slowest fires in existence. There is something deeply calming about that. A red dwarf does not rush. It does not flare into brilliance and vanish. It burns carefully, economically, almost endlessly. It reminds us that in the universe, longevity often belongs not to the strongest, but to the most patient. And yet, despite their calm nature, red dwarfs can be violent in another way. Many produce enormous stellar flares, sudden magnetic eruptions that can blast nearby planets with radiation. Some of the most powerful flares ever observed come from small red dwarfs, so even the smallest fires can erupt. That contradiction makes them compelling, gentle in lifespan, violent in moments, quiet in light, dominant in number. They are the background rhythm of the galaxy, the long-burning heartbeat of cosmic time. And because many exoplanets orbit red dwarfs, they may also shape the future of life in the universe. If life survives around stars, it may survive longest around these patient little suns. But some stars are stranger still, not because they burn slowly, but because they burn in ways we still do not fully understand. Not all stars shine steadily. Some pulse, swell, shrink, and brighten with rhythms so regular they almost feel alive. But among them, a rare few behave in ways so precise and strange that astronomers often describe them as stellar heartbeats. These are pulsating variable stars, and in some of the rarest cases their surfaces rise and fall like breathing, like circulation, like a cosmic pulse moving through a body of fire. It is easy to forget that stars are not solid. They are fluid spheres of plasma, held together by gravity and pressure, constantly balancing collapse against outward energy. That balance is not always stable. Sometimes the outer layers begin oscillating. The star expands, cools, contracts, heats, and repeats, a cycle written in light. Some of these rhythms are so predictable that astronomers use them as measuring tools across the universe. Cepheid variables, for example, pulse with periods directly linked to their true brightness, allowing scientists to calculate cosmic distances. Entire maps of galaxies depend on their heartbeat, but the strangest pulsators go beyond measurement. Some white dwarfs pulse internally, carrying seismic waves through their dense interiors. By studying those tiny brightness changes, astronomers can perform a kind of stellar ultrasound, reading the hidden layers inside. This field, called asteroseismology, has transformed how we understand stars. We no longer just observe their surfaces, we listen to their internal vibrations. It is one of the most intimate forms of astronomy. A star shaking reveals its hidden structure, like hearing the bones beneath skin. And there is something strangely human in that. A heartbeat means life to us. In stars, it means instability, pressure, and balance struggling to hold. The pulse is not weakness. It is structure adjusting itself to survive. That may be why these stars feel so alive, even though their rhythms are pure physics. They remind us that the universe has patterns of repetition everywhere. Beats, cycles, returns. Even in silence, stars keep rhythm. But some stars go beyond rhythm. Some spin so fast that they nearly tear themselves apart. There are stars that rotate so quickly that their shape changes under the force of their own motion, not slowly turning like the sun, but spinning at speeds so extreme that the star stretches outward at the equator, becoming wider than it is tall. These are some of the fastest spinning stars in the universe, and they live dangerously close to destruction. Imagine standing on the surface of such a star. At the equator, the ground beneath you would be racing sideways at hundreds of kilometers per second. The star would no longer be a sphere. It would bulge outward, flattened at the poles, swollen by its own momentum. Gravity would still hold it together, but only barely. This is what happens in B stars, rare hot stars spinning near their breakup speed. These stars rotate so fast that material can be flung off the equator into orbit, creating glowing disks of gas around them. In a sense, the star is shedding itself through motion alone, not because it is dying, but because it is spinning too hard to keep everything contained. That creates one of the strangest sights in astronomy, a star wrapped in its own spinning atmosphere. Spectroscopy reveals these disks clearly, showing hydrogen emissions unlike those of normal stars. The star becomes both source and surrounding cloud. Its motion reshapes its identity. Fast rotation also changes the inside. Material mixes more efficiently, altering the star's chemical evolution and lifespan. A rapidly spinning star ages differently than a slower one of the same mass. Motion changes fate. That is one of the great lessons of stellar physics. Speed is not cosmetic. It is transformative. And in some cases, if the star is massive enough, this rapid spin may set up one of the most violent deaths in the universe. A gamma-ray burst when the core collapses. That means the spin is not just a present condition. It may be preparing a future catastrophe. There is something unsettling about that. A star living on the edge of structural failure, held together by gravity while momentum constantly tries to tear it apart. It feels like tension made visible, a balance so precise that one small change could break everything. But perhaps that is what makes these stars beautiful. They survive at the edge. They show how close nature can come to chaos without falling into it. Yet even these spinning stars are not the strangest survivors, because some stars should have been destroyed by gravity long ago. but somehow remain suspended against collapse in ways we still struggle to explain. There are stars in the universe that live in a permanent argument with gravity. Every star does, in a way. Gravity pulls inward, trying to crush the star into itself, while pressure from fusion pushes outward, holding collapse back. That balance is what allows stars to exist at all, but some stars survive in far stranger ways, long after fusion should no longer be enough. These are the stars that seem to refuse collapse, balanced by physics so strange that they feel almost impossible. White dwarfs are one example. After a star like the Sun runs out of fuel, fusion ends. The outward fire is gone. By all ordinary logic, gravity should win immediately, but it does not. Instead, the star stabilizes through electron degeneracy pressure, a quantum effect that has nothing to do with heat or burning. It is a pressure born from the rules of particle identity itself. Electrons resist being compressed into the same quantum state. That resistance holds up the entire dead star. Think about that. A dead star supported not by fire, but by the architecture of quantum mechanics. It is one of the strangest supports in nature. Neutron stars take this even further. Their gravity is so strong that electrons and protons merge into neutrons, and now neutron degeneracy pressure takes over. Another quantum wall against total collapse. These stars survive not because they are alive, but because the universe has microscopic rules that scale into cosmic strength. But the balance is fragile. Add too much mass, and the support fails. The star collapses into a black hole, and that threshold is one of the great boundaries in astrophysics. It marks the line between strange survival and total disappearance. There is something profound in that. A star can die, lose its fire, and still resist the dark through invisible laws. Survival does not always look like life. Sometimes it looks like resistance. Quiet, invisible, fundamental resistance. But some stars resist collapse in even stranger ways, not by quantum pressure, but by magnetic force so intense it reshapes their entire structure. We have already met magnetars, the strongest magnets in the universe. But even ordinary white dwarfs can carry magnetic fields so powerful that they become strange in their own right. These are magnetic white dwarfs, and they reveal that stellar death does not erase complexity. Sometimes it concentrates it. A normal white dwarf is already extreme, Earth-sized sun mass, and supported by quantum mechanics. But magnetic white dwarfs add another layer of strangeness. Their magnetic fields can be millions of times stronger than Earth's. That field changes how matter behaves on and around the star. Gas falling onto the surface no longer spreads evenly. It follows magnetic lines, funneling toward the poles like rivers of fire. The star's light becomes polarized. Its atmosphere changes shape. In binary systems, these magnetic fields can disrupt accretion disks entirely, creating a special class of systems called polars. Instead of forming a normal disk, the stolen gas arcs directly along magnetic pathways onto the surface, creating bright hotspots and powerful X-ray emissions. The geometry of the system becomes dictated by invisible force. That makes these stars feel almost skeletal, as though magnetism is the hidden framework holding the strange behavior together. Their field is like an exposed nervous system, directing every movement of matter nearby. And astronomers still debate how these fields form. Were they inherited from magnetic stars before death, or intensified during collapse? The answer matters, because it connects stellar life to stellar afterlife. It tells us whether magnetism survives death, or is reborn by it. There is something haunting in that question. Can a star carry part of its identity beyond death? Magnetic white dwarfs suggest yes. Their fields are like memories preserved in collapse, invisible signatures of what came before. Even after fusion ends, even after the outer layers are gone, the hidden structure remains. or a kind of continuity through transformation. But if magnetic white dwarfs preserve memory, the next rare stars preserve something stranger, the ability to vanish almost completely, becoming so dim and cold that they blur the line between star and shadow. There is a strange kind of sadness in a star that no longer shines brightly enough to be noticed. Not because it is gone, but because it is still there, cooling, dimming, becoming quieter with time. White dwarfs begin their afterlife hot and bright, but over billions of years they fade, slowly, relentlessly. Their stored heat escapes into space, and their glow weakens. If given enough time, they would become black dwarfs, stellar remnants so cold and dark that they would be almost invisible, shadows of stars that once burned. But here is the strange part. The universe is not old enough for black dwarfs to exist. Not one. Every white dwarf ever formed is still cooling. That means black dwarfs are theoretical futures, ghost stars waiting for time that has not yet passed. They are predictions of a universe far older than the one we know. Imagine that. Entire categories of stars exist only in the future, objects that will one day fill the darkness, but have not yet had enough time to be born through cooling. It changes how we think about the sky. The universe is still unfinished. Some of its strangest objects have not arrived yet, and when they do, they will be the final state of countless stars like our sun. Cold embers in endless night. No fusion, no heat, no visible light, just matter and memory. There is something deeply peaceful about that idea. Not violent, not explosive, just a slow surrender to darkness across trillions of years, a star fading not in pain, but in patience, the long quiet after fire. It reminds us that endings in the universe are often softer than beginnings. A star is born in collapse and violence. It may die in expansion or explosion, but afterward it simply cools, like a room after music ends, like breath slowing after a long day. But not all fading stars are calm. Some become unstable as they cool, and in that instability they reveal hidden layers of their past. Death does not always bring stillness. Some white dwarfs tremble. They vibrate with internal waves, their dense interiors ringing like bells in the dark. To the eye, the changes are tiny. Small shifts in brightness, subtle pulses in light. But inside, the motion is immense. These are pulsating white dwarfs, and they are among the most useful strange stars in modern astronomy. A white dwarf may look simple from the outside, small, dense, cooling. But inside it carries layers of carbon, oxygen, helium, and sometimes hydrogen, stacked by its past life. As it cools to certain temperatures, parts of its outer layers become unstable. Pressure waves form, gravity waves move through the interior. The star begins to oscillate, not violently, but rhythmically. Each vibration carries information about internal structure. By measuring these pulses, astronomers can reconstruct the star's hidden layers, its mass, temperature, and even how much of it has crystallized inside. It is like listening to an instrument to understand its shape. This is one of the most elegant techniques in astronomy. The dead star speaks through vibration. Its trembling becomes data. Its instability becomes knowledge. And what we have learned is remarkable. Some white dwarfs are far more complex inside than once imagined, with crystallized cores, layered atmospheres, and thermal histories preserved like geological records. A white dwarf is not just a remnant, it is an archive. Its pulse is the sound of memory moving through dense matter. There is something beautiful in that. Even after death, the star still has a voice, not a bright one, not a violent one, but a quiet rhythm, a subtle signal carried through darkness. It reminds us that silence in the universe is often only silence to those who do not know how to listen. But there are stars even stranger than trembling white dwarfs, because some stars are so rare, so chemically unusual, that they seem to rewrite the normal recipe of stellar life itself. Most stars follow a familiar recipe: hydrogen first, helium second, and deeper inside, heavier elements form through fusion as the star ages. That pattern is so reliable that astronomers use it as a map to understand stellar life. But some rare stars break that recipe entirely. Their surfaces are filled with elements that should be hidden deep inside, or missing elements that should be everywhere. They're chemical anomalies, stars that seem to have rewritten their own ingredients. One of the strangest examples is the hydrogen-deficient star. Hydrogen is the most abundant element in the universe, and almost every normal star wears it on the surface like skin. But a few rare stars have lost it almost completely, exposing deeper helium and carbon-rich layers to space. And that is deeply unnatural by normal standards. It suggests a violent history, perhaps a merger between two white dwarfs, or a late thermal pulse that peeled the star inside out. These stars carry exposed chemistry like scars. Their surfaces tell stories of disruption. Some stars are rich in lithium, an element usually destroyed inside stellar interiors. Yet somehow it reappears in strange abundance, forcing astronomers to rethink mixing processes and internal fusion pathways. Others show unusual heavy elements, signatures of neutron capture reactions that hint at rare nuclear events in their past. In astronomy, chemistry is memory. Every element on a stellar surface is evidence. It tells us what the star has done, what it has survived, and sometimes what it consumed. That is why strange chemistry matters so much. A chemically unusual star is like a confession written in atoms. It reveals hidden chapters no telescope could see directly, and there is something deeply comforting in that idea. That history leaves traces, that even when events are invisible, their effects remain written into the surface. Rare stars remind us that nothing in the universe happens without leaving marks. Even light carries memory. But some stars are stranger than unusual chemistry. Some are so heavy, so unstable, that they live on the very edge of self-destruction from the moment they are born. There are stars so massive that peace is impossible for them. From the moment they ignite, their lives are a battle against their own size. These are the hypergiants, stellar giants so enormous and luminous that they burn through life at reckless speed. If stars like the sun are candles, hypergiants are wildfires. They can carry more than 100 times the sun's mass and shine millions of times brighter. Their cores are furnaces under unimaginable pressure, burning fuel so rapidly that their lifespans shrink from billions of years to only a few million. That sounds long to us, but in cosmic terms it is almost nothing. They are born already racing toward death, and because they are so bright, radiation itself becomes a problem. Light pushes outward with such force that it can blow away the star's own outer layers. These stars are literally being torn apart by their own brilliance. Their surfaces become unstable, swelling and shrinking, shedding vast clouds of gas into space. Some lose enough mass to transform into entirely different types of stars before they die. Hypergiant is not stable identity. It is continuous transformation under pressure. The famous red hypergiants are among the largest stars by size, so enormous that if placed where the Sun is, their outer atmospheres could stretch beyond the orbit of Mars or even Jupiter. Yet despite that vastness, their outer layers are thin and fragile like enormous glowing fog. Inside, the core races through fusion stages, building heavier and heavier elements toward collapse. Every day is acceleration. Every moment is tension. These stars matter because they are factories of heavy elements and future supernovae. Their deaths enrich galaxies. Their lives shape surrounding space through radiation and stellar winds. They are architects of cosmic change simply by existing. But emotionally, hypergiants carry another lesson. Our great size comes with instability. Great brightness comes with cost. They live intensely, brilliantly, but briefly. They are stars that cannot afford calm. Their existence is motion toward ending. And perhaps that is why they feel so dramatic. They remind us that power is not peace. Sometimes the brightest lives burn the fastest. But there is a rarer kind of giant still, stars so luminous that they can briefly outshine millions of suns, only to vanish behind their own instability like cosmic mirages. Some stars are born so luminous that their own light becomes a threat to their survival. Imagine a star shining with millions of times the brightness of the sun, flooding space with radiation so intense that the outward pressure nearly overpowers gravity itself. These are luminous blue variables, and among the rarest and most unstable stars in existence. They are giants trapped in a permanent state of imbalance, too massive to stay calm, too bright to remain stable. Their lives are defined by eruptions. Unlike ordinary stars, which spend long periods in predictable phases, luminous blue variables can suddenly brighten, expand, and throw huge amounts of mass into space. It is as though the star briefly loses control of itself. The surface swells, the winds strengthen, and layers are expelled outward into the surrounding darkness. These eruptions can make the star appear dramatically brighter, but underneath, the deeper instability remains unresolved. The strange thing is that these eruptions are not the end. The star survives. It continues living after shedding enormous pieces of itself, but every eruption changes its future. It becomes lighter, hotter, and often stranger. A luminous blue variable is a star rewriting its own fate in real time. Some of them may be preparing for supernova collapse, while others may survive longer than expected. That uncertainty makes them important. Astronomers watch them closely because they may reveal what happens in the final, unstable years before stellar death. Their winds shape enormous nebulae around them, giant glowing shells made of their own discarded material. A star surrounded by its own history. There is something haunting in that image. A living star walking inside its own remains, carrying evidence of past instability like footprints in gas. It reminds us that even the brightest things in the universe can struggle to contain themselves, and sometimes survival means letting part of yourself go. But there are stars stranger still. Stars that shine not because they are large, but because they are unbelievably hot. Brightness and heat are not always the same thing. A large star can be bright simply because it is enormous. But some stars are small and still burn with temperatures so extreme that their surfaces become almost unimaginable. These are the hottest stars in the universe, stellar remnants or stripped cores whose heat reaches hundreds of thousands of degrees. For comparison, the Sun's surface is about 5,500 degrees Celsius. These stars can be 50 times hotter, sometimes more. At those temperatures, the physics of light changes. Most of their radiation shifts into ultraviolet and X-rays, invisible to human eyes. If you could somehow stand near one, which you could not survive, the heat would not feel like warmth. It would feel like annihilation. One class of these stars includes the exposed cores of dying stars, left behind after outer layers drift away into planetary nebulae. What remains is a blazing core, still carrying the heat of collapse and fusion history. These stars are temporary. They cool into white dwarfs over time, but during this phase they are among the hottest visible objects in the galaxy. Their radiation ionizes surrounding gas, making nebulae glow in brilliant colors. In a sense, the star paints the space around it with heat. Another class includes rare stripped helium stars and certain Wolf-Rayet stars, whose exposed fusion layers burn at extreme temperatures. They reveal what lies beneath the surface of ordinary stellar life, hidden engines suddenly visible. What makes these stars fascinating is how intense they are despite their small size. They remind us that size is not the only measure of power. Sometimes the most concentrated things are the most extreme. A small core can outburn giants. A stripped remnant can become hotter than the star it once was. There is something elegant in that reversal. Loss creating intensity. Reduction creating power. These stars are like exposed truth. Nothing hidden. Everything concentrated into pure heat. But even the hottest stars are temporary. Because in the end, temperature fades, and what remains may become something colder, stranger, and quieter than fire ever was. Not every star in the universe announces itself with brightness. Some of the strangest stars are powerful, active, and alive by every physical definition. Yet to human eyes they would seem almost invisible. Their energy is there, but most of it escapes in wavelengths our eyes cannot catch. These are the ultra-cool stars, the dim red and infrared burners that quietly dominate the galaxy without ever becoming famous in the night sky. It is strange to realize that brightness is not the same as importance. We are naturally drawn to luminous things, giant stars, brilliant explosions, glowing nebulae. But most stars are not like that. Most stars are small, cool, and quiet. Some barely shine in visible light at all. Their surfaces are so cool by stellar standards that much of their energy slips into infrared radiation. To us, they are nearly invisible. But in number, they rule the galaxy. The strangest part is how efficient they are. These stars waste almost nothing. Their fusion burns slowly, then carefully, stretching their fuel over unimaginable spans of time. While giant stars race through their lives in millions of years, these faint stars may endure for trillions. That means long after bright stars have vanished, long after galaxies change shape and the universe grows older, these tiny dim stars may still be burning. Quiet survivors of cosmic time. Some of them also blur into the territory of brown dwarfs, the failed stars we met earlier. That boundary between the smallest true stars and the largest failed stars is one of the most delicate borders in astrophysics. A tiny difference in mass decides whether hydrogen fusion begins or never truly starts. Such a small difference. Such a huge consequence. There is something deeply calming in these stars. They remind us that quietness is not weakness. Yet that dimness is not insignificance. Some of the longest-lasting fires in the universe are also the faintest. Their lesson is patience. Their existence is endurance. But some stars are not patient at all. Some erupt in flashes so sudden and violent that they seem to wake the galaxy itself. Most stars change slowly. Their lives unfold across millions or billions of years, too slowly for human eyes to notice. But a rare few break that rhythm. They flash, flare, and erupt in moments, releasing enormous energy almost without warning. These are flare stars, and they are among the most unpredictable stars in the sky. A flare star is usually small, often a red dwarf, but inside it carries intense magnetic tension. The star's magnetic fields twist, tangle, and build stress over time. Then suddenly, like a snapped wire, that stress releases. A flare explodes outward. Radiation surges. The star brightens dramatically in minutes or even seconds. Some flares are so powerful they release more energy than the largest solar storms ever recorded from our Sun. And because many exoplanets orbit very close to red dwarfs, these flares matter deeply. A nearby planet may be hit by repeated storms of radiation, stripping atmospheres or altering chemistry. That means the mood of a small star can shape the possibility of life around it. Quiet star, violent weather. It is a strange contradiction. These stars may look calm most of the time, small, faint, harmless. Then suddenly they erupt like lightning in the dark. That unpredictability makes them important to astronomers studying planetary habitability. A planet in the right temperature zone may still be unlivable if its star is too unstable. The star becomes climate, weather, danger, and fate all at once. There is something emotionally familiar in flare stars: calm surfaces hiding sudden storms, long stretches of peace interrupted by violent release. They remind us that stability is sometimes only temporary tension waiting for a trigger. But in the universe, even these flashes are part of survival. The magnetic field resets, the star continues, the storm passes, and the light remains. Yet even flare stars are not the strangest temporary lights, because some stars flash only once, in ways so brief and rare that astronomers can spend entire careers waiting to see them. Some events in the universe happen so quickly that if you blink, you miss them forever. A star can spend millions of years preparing for a single moment, and that moment may last only seconds. That is one of the strangest imbalances in astronomy: endless preparation for a brief explosion of truth. Some rare stars reveal themselves this way, through a single sudden flash that changes everything. One example is the helium flash, a hidden event inside aging stars. When a sun-like star expands into a red giant, its core contracts and heats until helium fusion ignites. But unlike normal fusion, the core is supported by quantum pressure, which means temperature can rise without expansion to cool it. The result is a runaway burst of helium fusion deep inside the core. The energy release is enormous, but almost all of it is absorbed internally. From the outside, the star barely changes. Imagine that, one of the most violent internal transitions in a star's life, and no visible fireworks at all. A private explosion, a hidden turning point. Other stars reveal themselves through visible flashes, rare stellar mergers, final helium shell pulses, or sudden luminous outbursts from unstable remnants. These events can transform a star's chemistry, brightness, and future in a matter of days. A long life rewritten in one moment. That is what makes these rare flashes so important. They are transition points, tiny windows where the future changes direction. Astronomers wait years, sometimes decades, to catch them, because to witness one is to see stellar evolution moving in real time, not as theory, not as simulation, but as living change. There is something deeply moving in that. A star can spend nearly all of its existence in quiet preparation for one brief moment of transformation. It reminds us that time is not always evenly distributed. Sometimes everything changes at once. But some stars are stranger still, because instead of flashing once, they vanish and return, as though crossing the border between existence and absence. The night sky feels reliable. Stars rise, shine, and remain. That stability is part of why they comfort us. But some stars break that promise. They fade so dramatically that they seem to vanish, only to return later as though nothing happened. Not dead, not gone, just hidden. These are disappearing variable stars, and their behavior feels almost supernatural until physics explains it. Sometimes the cause is dust. While material thrown off by the star cools and condenses into clouds that drift into our line of sight, blocking the light. The star is still there, burning exactly as before, but for a time it becomes invisible to us. Then the dust moves on, and the light returns. In other systems, the disappearance comes from eclipses, companions, disks, or strange orbital geometry hiding the star for long stretches. In rare cases, the dimming can be extreme, reducing the light by more than 90%. To an observer, it feels like erasure, but it is only concealment. What makes these stars fascinating is what they teach us about perspective. The star itself may not have changed at all, only our view changed. That is enough to transform reality from our side. Astronomers study these events carefully because the dimming patterns reveal hidden companions, circumstellar disks, and the structure of stellar winds. In other words, disappearance becomes a tool of discovery. What hides the star also reveals deeper truth. There is something beautiful in that reversal, absence becoming information, darkness becoming evidence. It reminds us that not seeing something does not mean it is gone. Sometimes it is simply waiting behind a curtain of dust, shadow, or angle, still burning, still present, still real. And perhaps that is one of the gentlest lessons rare stars offer. Disappearance is not always ending. Sometimes it's only distance, only obstruction, only time. But there is one final kind of rare star we must meet, a star so strange that it may represent the future of the universe itself, the longest, slowest, and quietest form of stellar survival imaginable. Sister Kund, if you could travel unimaginably far into the future, beyond the rise and fall of civilizations, beyond the lifetime of the sun, beyond even the age of galaxies as we know them, you would find a quieter universe, a darker universe, and in that distant future, the stars most likely to remain would not be the giant brilliant ones we admire today. They would be the smallest and slowest burners, red dwarfs. These tiny stars may be the final long-lived fires of the cosmos. Red dwarfs burn fuel with extraordinary patience. Unlike larger stars, they mix their hydrogen efficiently throughout their entire interiors, meaning almost nothing is wasted. Every piece of fuel is eventually used. That gives them lifetimes measured not in billions, but trillions of years. Longer than the universe has existed so far. In fact, every red dwarf ever born is still alive today. Not one has had time to die naturally. That means when we look at them, we are not seeing endings. We are seeing futures. They are previews of the farthest chapters of cosmic history. Long after stars like the Sun become white dwarfs, long after massive stars explode and vanish, red dwarfs will continue glowing quietly in the dark. Their light may become the dominant starlight of the late universe. Imagine a cosmos where the bright giants are gone, the dramatic supernovae are rare, and the sky is ruled by small, dim, patient fires. It feels quieter, older, slower. There is something deeply peaceful in that vision. The universe growing old not with violence, but with persistence. Not with brightness, but endurance. Red dwarfs remind us that survival often belongs to the small and careful. Not the powerful and fast. They are the final candles of time. But even they will not last forever, and when they fade, the universe will enter an age stranger than anything we know now. What happens when the stars are gone? It sounds like the end of everything. But in cosmology, endings are often just transitions into stranger forms of existence. If enough time passes, far more than the current age of the universe, most stars will have burned out, exploded, or cooled into dark remnants. The bright era of stars will end, and what remains will be a universe of leftovers, white dwarfs cooling toward black dwarfs, neutron stars drifting through darkness, black holes slowly consuming stray matter, brown dwarfs fading colder. The sky, if there's still anyone to see it, would be almost empty of new light. The age of active stars would be over. This future is sometimes called the degenerate era, because matter itself remains, but in dead or nearly dead forms. No fresh fusion, no newborn stars, only remnants. Yet even in this dark future, rare interactions may still create brief light. White dwarfs colliding, neutron stars merging, black holes feeding, tiny flashes in endless darkness. The universe would not be fully dead, just quieter than we can imagine. It is a humbling thought. The stars we know are temporary. Even the galaxy itself is passing through a bright chapter that will not last forever. But perhaps that makes tonight's sky more meaningful. Every star above you is part of a temporary era of light, a brief golden age in the history of the cosmos. We are living inside it now. Rare stars make that truth even clearer. They are the exceptions, the strange experiments. The unusual survivors that show us how flexible the universe can be. And in their strangeness, they reveal the larger story. Nothing stays the same forever. Not stars, not galaxies, not even the bright age of the universe itself. But before everything fades, there is still one final mystery. A question hidden inside all rare stars. A question not about how they live or die, but why the universe keeps making exceptions at all. By now, the pattern has become impossible to ignore. The universe creates rules and then it creates exceptions. Stars are supposed to follow predictable lives. Birth from gas, balance through fusion, death by mass. That is the textbook story. Clean, ordered, reliable. But rare stars refuse to stay inside that story. They steal from companions, they crystallize after death, they pulse like hearts. They spin like storms, they hide behind their own dust, they explode and survive, they expose their inner layers long before death arrives. Again and again the universe produces stars that bend the expected path, and perhaps that is the deeper truth of astronomy. The rules matter, but the exceptions teach us more. Ordinary stars explain how nature works. Rare stars show when nature becomes creative. They reveal the edges of physics, the boundaries of stability, the places where gravity, magnetism, quantum mechanics, and time collide in unexpected ways. A neutron star shows how matter behaves under impossible pressure. A magnetar reveals the violence of concentrated magnetic force. A blue straggler teaches that age can be rewritten by collision. A white dwarf shows that death can cool into crystal. Every rare star is a question disguised as an object, and astronomers love questions more than answers, because answers close doors, questions open them. That may be why rare stars matter so much. They remind science to stay humble. Every time we think we understand stellar evolution, the sky presents another exception, another object that should not exist but does, another light that behaves differently than expected. The universe keeps surprising itself, and us. There is something deeply comforting in that. Reality is not rigid. It is flexible, layered, and full of unexpected paths. Not everything follows the simplest route. Not everything ends where it should. Some things survive by changing, some by enduring, some by becoming stranger. Rare stars are proof of that. They are the universe's way of saying that even in systems governed by laws, there is room for surprise, room for unusual survival, room for strange beauty. And perhaps that is why they feel so calming to think about at night. Because they remind us that being unusual does not mean being wrong. Sometimes it means carrying truths others cannot yet see. But there is one final thing rare stars reveal. Something quieter than physics, deeper than chemistry, and older than light itself. When people look at the night sky, they often search for peace, a feeling of distance from daily life, a reminder that the universe is larger than worry. But rare stars offer something even more specific than peace. They offer perspective, because the strangest stars in the universe teach a simple truth. Existence is far more flexible than it first appears. A star can die and keep spinning. A star can cool into crystal. A star can lose itself and become hotter. A star can hide behind dust and return. A star can survive violence, theft, collapse, and instability, and still remain part of the story. That is what makes rare stars so strangely comforting. They are proof that unusual paths are still natural paths. The universe does not only make simple things, it makes exceptions. It makes survivors. It makes strange continuations after endings. And perhaps that is why the night sky feels healing, because above us is a record of endurance. Not perfect endurance, not peaceful endurance, but real endurance. Stars surviving through transformation, through collapse, through change. Rare stars remind us that change is not failure. Instability is not weakness. Transformation is not disappearance. The sky is full of lives rewritten by pressure, by time, by closeness, by loss, and yet the light continues. That may be the most relaxing fact of all. Not that the universe is simple, but that it is resilient, that even its strangest objects still belong, and tonight, as you rest beneath that sky, perhaps that is enough. To know that somewhere out there, a dead star is still pulsing like a perfect clock. Somewhere, a white dwarf is slowly turning to crystal in silence. Somewhere, a tiny red dwarf is burning with patience that will outlast almost everything. And somewhere, a rare star is doing something no scientist expected, quietly reminding us that mystery is not a flaw in reality. It is part of its design. So let the stars above soften your thoughts tonight. Let their strange stories carry the weight of wonder for you. Let the scale of their lives make your own worries feel smaller, lighter, quieter. Because the universe does not ask you to understand everything, only to look up, breathe, and remember. Even the strangest things in existence still have a place in the sky. And now, as the rare lights of the cosmos continue their endless work in the dark, you can let your mind grow still, your breathing slow, and your thoughts drift gently outward, into that vast and patient universe where even the strangest stars are simply part of the night.